to give a talk on science and scientific research in Python, which at least some of you have decided that's an interesting topic, so thank you for hanging out. And I also looked at my the timing and saw that I had 40 minutes, and everyone's been taught by Ted that you're only supposed to talk for 18 minutes, or then people go to sleep. So what I've done is I actually have 2 talks smashed together, so we can change topics so you'll stay involved. Okay. But I'll get to that. So I want to talk a little bit about scientific Python and like some of the issues, like the challenges and successes of Python in the scientific community. But I also want to talk about going forward as a community and what are the challenges that bind us as a community that we have to face going forward to keep the community alive and well. And I realized that I did have a slide that showed Leah and James. So Leah and James are in the back here. I want to first say a big thank you to Leah and James. They're the ones who make sure that these PyData conferences actually happen. So let's give them a round of applause. Without these 2 fine folks, like none of these conferences would happen like clockwork, and we really appreciate that. So first about me. So Andy Terrel, I'm Chief Science Officer at Continuum Analytics, and also I'm President of NumFocus, which means I get to talk and send a lot of emails and code some, but not as much as I'd like. My background comes from high-performance computing and kind of worked with computational mathematics and finance and different simulations and things like that. To make that a little more real, the kind of problems I've always solved in academia have always looked like this, where you have some math equations. For example, here we take the Euler equations, which is the fluid, kind of the basic of modern compressible fluid dynamics, incompressible fluid dynamics. And typically we take those math equations, which is a great abstraction, but very hard to really communicate with the entire population of the world. So that sort of thing, while it works really well for a technical audience who've had lots of training, we often have to turn that into something, 1, that the computer can understand, and 2, that other people can understand so that we can solve real problems. And so you go to the 2 axes there. I'll work with, for example, visualizations. And in this case is a 1D simulation of surface of water at a gauge height, and supercomputers, and working on very massive computers to make sure that you can take that 1D problem and scale it up to a real 2D problem in this case, and solve and it's kind of hard picture to see, but down here on the bottom right is solving, for example, a hurricane storm surge, which has a massive effect on everybody's life. And so going from that very technical problem to the stages to actually have actionable insights to help the government or businesses determine their paths, such as, do I actually put my house out on Long Island, for example, which is a real problem people have. So that's kind of like my academic life and where the research came from. Now big data kind of happened, and they have the similar sorts of problems, and I often work now in often in a little bit pivoted workflow, where I'm taking unstructured data and taking data off of the open web or open, like the big data deluge. People are just having a huge, massive problem of just handling all these things. And the same thing going to algorithms, for example, machine learning algorithms, where they have the scikit-learn decision algorithms there, and also, for example, much smaller computers these days. Used to work on 16,000 cores. Now I get 100, and they look like this in comparison. I actually Googled Hadoop supercomputer, and that's the picture I got. So Raspberry Pis. So they really focus on scale-out technologies and not very many scale-up technologies. And whereas in previous life, you had to have both, or else you were dead in the water. And then finally, a lot of Peter mentioned some of the DARPA work we've done, and in this same kind of way, making business decisions, although for the Department of Justice on helping find human trafficking victims and things like that. And so data science has a lot of potential in pretty much every facet of our lives. And so I kind of go through some of the more like the path it takes that research into actual production, actual getting things done. So Peter talked a lot about his Venn diagram, and so in lieu of the competing Venn diagrams, I pulled out Drew Conway's. And so I like to talk about data science. So this is data science, but also computational math is very similar, where you have some hacking skills. You have the ability to actually get things done on a computer. You have math and knowledge, so being able to do real abstract thinking about what's actually going on in your computer and be able to communicate it with each other and develop interfaces and abstractions well. And then I think that one thing that a lot of people miss is like actually doing substantive expertise. So you can have hacking skills in math, and that's kind of machine learning, but if you don't have that substantive expertise of actually solving real-world problems and coming and getting into that messiness of data and things like that, that's when data science, in my mind, becomes really a lot of fun, but also kind of the moment where you can really make a big impact on society as a whole. But of course, we also have, everybody knows those guys who are in this, quote, danger zone over here, who have lots of expertise, no math background, and just code. And those guys are fun. Really. Drew likes to call it danger. I like to call it fun. But so in this kind of realm of like actually getting together as a community to build these things out, we started this foundation called NumFocus. And NumFocus essentially came from a group of scientists who were working together, who were spreading out over companies already, and actually looking at, hey, all these companies, all these government projects and academics are using our code, but nobody's really there to like build the base and make sure that it continues in a substantial way. And so NumFocus has one simple goal: is to sustain open science through open code. In that goal, so that everybody, businesses and academics and everybody can play in this PyData ecosystem, and we've expanded to Julia and R as well, so that we actually give data science a home that's actually supported and can continue throughout the future. If you go to our website, you'll see this nice banner where we have kind of breaks down kind of our activities from projects, and I'll show you a list of projects in a second, to education such as our John Hunter Technical Fellowship, or in our Women in Technology programs, because we have a very strong desire to make sure that we have a diverse ecosystem of contributors in our systems. Fiscal sponsorship for all you guys who, this is Dallas, so there's plenty of money, right? So so all you guys who want to help us sponsor these projects and help projects who need money to actually work and get their features out and things like that, we definitely help a lot of open source projects connect with people who can sponsor them. And also PyData, which we're all at here today. Here's a list. Here's a kind of a list of the projects we kind of touch on. From a lot of us started in the Python world, but we have R OpenSci, for example, and Julia, the next greatest data science language. As soon as just don't switch, but you can use them together. It's pretty nice. And then also from education, so like for example, our Insight blog posts, or data carpentry and software carpentry to help educate the next leaders in data science and so on. Here's a list of people. You go to our foundation page, you can see all their names. Academics, well-known, for example, the IPython team, Brian and Fernando, and then people in government labs and companies and so on and so forth. So a real kind of mix of folks to help build this foundation. Okay, so that's the kind of intro and kind of pitch of who we are, why I'm here, and what I'm, where, so you kind of know who I am. So I want to kind of start by talking about, researchers using Python. Where did it start? Why are we starting to use Python? What are the kind of major modes that kind of get us into this language? For me, it started with this book by Hans-Peter Langtingen, and on this, you can't really see the slide, the picture of the book at all, but the book was called Python Scripting for Computational Science. And essentially, it was Python for Fortran writers. And I mean, it was amazing, because it was way before NumPy existed, and it was this idea that you could have a single program that would call your Fortran and your GNU plot, and everything would just automatically work, and you can make it hit supercomputers and all sorts of fancy stuff. And it kind of blew my mind a little bit, because at the same time I was struggling with getting all my codes to even work, much less get them to do the entire cycle in one script. So Hans-Peter kind of identified a lot of kind of different ways to use Python in the scientific workflow. And I kind of broke them down in my viewpoint is that there's kind of different modalities inside like Python in the research world, such as, first off, there's kind of Python as a programming language and helping people become better at their job as a better programming language does. The second kind of we talk about is like it's kind of glue. Some people call it super glue. And so a lot of people call it scripting language. Scripting language is kind of a pejorative term in the programming language world, meaning it's not a real programming language, but it's something you just kind of do off the side. But at the same time, we know that Python can do a lot of real work, and it does. It runs some of the biggest corporations in the world and runs some of the most innovative labs in the world. But at the same time, the fact that it can talk to everybody, the fact that it can get objects from Java or from C and actually make them cooperate together is a really important process. Another kind of modality is the delivery of like very complicated analytics engines. Every time I see somebody get up and talk about Hadoop and show me word count, a part of me dies. Because Python has such a great ecosystem of libraries where people have come together to solve really complicated math to solve these problems into the ecosystem, and Python really does a really good job of helping them put that together and deliver it forward. Question? Yes. Yeah. I will, and I'll go through them in just a minute. But so yeah, I have plenty of examples. Yep. And finally, kind of near and dear to my heart is Python is a really good domain-specific language. So you can really embed a lot of knowledge into that in Python to give a deeper interaction with the domain. So first off, so I'll go through these various modalities with some case studies, and then next side of the talk, I'll talk about some of the challenges we have in the community. So the first kind of one is how can the programming language help your job? I think I hear this a lot from researchers, because a lot of researchers still will use, oh, well, Fortran's fast and it does my complex analysis well. Or MATLAB is good enough for me and I don't have to worry about handling any of that open source stuff. Or I hear, for example, no, I need Java because it's got all this help, this type safety and things like that. And so like this whole idea of like, how does a programming language actually help you do your job rather than you just programming on the language? And I think that the one thing, I don't have a lot of examples here, but the one thing I will say about Python for a researcher is it doesn't get in your way. You can write a Python script very quickly and do a lot of things in a very short amount of time, but also drive very complicated things at the same time. So in some sense, my view is like get the programming language out of my way as quick as possible, but also let me kind of describe what I need done at the same time. And I think the other thing, so Ken Kennedy at University of Houston had this, or no, he was at Rice, I'm sorry. Thank you. Well, smaller, yeah. It's like 20 miles. But Ken Kennedy at Rice had this concept of a telescoping language, and like he chased this program for a very long time of developing languages that you could write at one level, at a very high level, such as like Java or something that you could describe. Okay, so he's a Fortran compiler, so Java was way high level to him. Or down to the very low level, which is assembly or something, and being able to take touch points in between it. Python as a language is able to do that very well, where you write Python at a very high level, and there's many different ways to get down to that very low level programming to get those complex engines working, such as working with Python to go to C, or PyASM if you want to generate just assembly code, or the Py4j if you want to drive large Java programs and things like that. So Python actually, as a language, it does both the glue, but it also does lowering it down to the bare metal. And I realize now that I should have shown Ken Kennedy's big slide on that, but it's a very important concept. But that being said, I like to solve big problems, so I want to show you guys a little bit about how you build a flexible system for solving very complex analytics. And I think one thing about science that's different from business is that the appetite for just changing out your analytics very quickly, at least in your researchers day to day, and then moving to an operational day to day. And I think the businesses have the same idea that they want to drive innovation, but then they want to build an operational process. So there's a question earlier about how do we deal with the fact that everything's changing? But in science, very often you want things to change because that's how you get to better processes. So the first example I have is this code called PyLith. It's built by USGS that I had some hand in helping, very minor hand. But it's an earthquake simulator. And so it's a very typical problem that you have in science where I have some, in this case, I have some domain, I have a point of interest in that domain that has a lot of activity that has an effect throughout the rest of the domain. In this case, it's a fracture, right? So the earth fractures, and there's a lot of stress right in that middle. And that's what the nice red part there is like where the maximum stress is. And then you want to see how this affects the rest of the ecosystem, in this case the earth, and see how many buildings it knocks down or something like that. But the thing there is that it's not a single problem. And the real cause of the problem is this dynamic rupture. But really what actually affects everybody is this like what we call it quasi-static relaxation. So the fact that this pressure is going to be released throughout the earth. And that's actually what's going to knock down your buildings or cause a lot of earthquake damage and so on and so forth. And so even being able to couple these systems is a very difficult thing to do because those are two very different types of physical characteristics. And so you have multiple models, you have different ways of, so I have multiple meshes, but that's basically different ways of cutting this problem and slicing it and figuring out which part do I solve first and how do I make that work. And then also it has to be parallel, and these are big problems, so they have to be highly coupled. And so it's a very challenging problem. To give you a quick example of that flexibility, one thing we looked at is like how do we generate, how do we couple all these systems, but for example, there's this kind of, let's call it a heated discussion, which is a nice academic way of saying drag down, knockout fight over whether you should use triangulars or rectangles. It's like, how stupid is that? But the mathematics around it becomes like just volumes have been published on this issue. So what we did is create a Python code that actually tests it because we're tired of getting in these academic fights. We was like, you know what? We're going to write a code that actually lets us implement very high level, say, I want a triangle or I want a rectangle. And since we built a system that kind of handled both the mathematics and the domain decomposition well, it actually was very flexible and interoperable. And Python allows you to, lets the scientist just write triangle or rectangle, but what he's really driving is a much larger architecture that looks like this, where that top application layer, he might say, I want a rectangle. It pipes off to a symbolic engine. My favorite one's SymPy. I did have some help some folks write that. We have one of the core authors here in the audience, Aaron here. And so we pipe off to the symbolics that actually takes those equations and now substitute all the rules of, all right, you have triangles, here's what your basis functions looks like. Oh, you have rectangles, this is what your basis functions looks like. So it comes back and gives me math that then I can pass off to a linear solver and also build out the data structures. So a rectangle looks a lot different from a triangle, and the data structures in order to interact with them actually change quite a bit. And then from that, go to a linear solver. So Petsy's my favorite linear solver. And we pass up. So that'll solve the big, large equations, but NumPy comes back as the data structure to pass to that application that they can actually do the visualization on, or the other systems on. So NumPy becomes a really nice vehicle for going from that parallel intent solver to something that the application can use. And then we also have other processes that we can use, for example, PyCUDA on, and use on a GPU or something like that. And so this kind of notion of an application touching all these different pieces, and these are all large codes. I think every one of the codes up here is probably at least, I think SymPy is only like 30,000 lines, but I think the rest of them are like at least 100,000, 400,000 lines type codes. And so these codes are very large codes, but since they interoperate with Python, the application doesn't have to care so much about all the details, and the Python language takes care of a lot of those things. So this is an example of doing, in the research world, of touching all these things. But you can also do interesting parts, like for that equation definition, I can actually change out my equations into a different form. So mathematicians can play and get a different formulation of those equations. And then linear algebraists can play because they can give us different ways to solve linear algebra in the Petsy routine and things like that. So it becomes a way that not only are we leveraging Python's ability to glue, but we're leveraging the expertise of many different communities. So that's great, but how about a real-world application? Because the application I showed wasn't, so it's sort of real-world, but it's still just boxes and whatnot. So I had the privilege of working with the geoclock community. And what they do is, one of their big applications is predicting tsunamis. And the way they kind of handle this is that they have grids all over the, they hit a grid all over the ocean. So when you have a tsunami event, they can track the shock of the water throughout the world. And this is an example of the Chilean tsunami. And here, like the grids, the actual big open grids are actually refined much lower, but if we showed the grid, you wouldn't be able to see the actual effect. And so this is a very real-world event that could then be help used to predict the surge water. And the way this guy was built, and it's a very old code, and so if in here you have, oh, you can't see colors at all on that screen. Okay. But up here on the top right, you have the clawpack kernels. And the clawpack kernels is a code from the 70s. I mean, 80s, I guess. Depends on exactly when you count whether it was written in grad school or not. But written by Randy Levesque in Fortran, a very old style. Like all the books teach dynamic shocks out of his book. So you have these kernels, but now we want to scale it up to the machines of today. And the way we do that is through this Python layer, where we can talk to this whole Fortran library, and once again pass off to my favorite linear algebra library, PETSI. And PETSI actually then talks to the machine. So then Python, while it doesn't have to be the driver of your big data analytics, it can certainly be the driver of something else that's a big data system or a parallel system, and so on and so forth. And so that's another kind of example out in the wild where the PyClaw and GeoClaw communities. And kind of my final example, well, I guess I have two more examples. Well, another example is, what about capturing that beauty of that mathematics? So another project that I worked on in grad school is called the Phoenix Project. And what they kind of came to the conclusion of, they were mathematicians who who would formulate lots of mathematical equations. So everyone likes to talk about the old joke. If you have an engineer and you ask them to boil water, they'll give them water in a pan, and they'll pull it in the pan and stick it on the stove and turn it on and let it boil. Then a mathematician comes in and they say, all right, boil water, and he's like, well, here's a pan of water, thereby reduce it to a previously known problem, and they give it to the engineer. Timing didn't work. So but the same thing happened with the Phoenix Project, where you have all these mathematicians they've proposed lots of ways to solve these problems. For example, here's a heart with lots of mechanics that go into defining how domains happen in the heart and what actual equations to use. The heart's a funny one because it doesn't make sense that you turn off blood flow and then electricity turns off. So it's like somehow it would be like you turn off your faucet and all of a sudden your lights go out. And so there's a really interesting coupling going on in the heart. And so like it's boggled the mind of researchers for many years. And mathematicians have lots of models for doing it, but there's not very many ways to actually get those into code. So if I have 50 models and I'm the guy who has to code them, I usually pick one, and if I get that done in a year, I'm good. So they wanted to come out and look at how do we get this adaptivity and error control, and they chose Python. And so it typically works like this. So this is the hello world of PDEs. It's called the Laplacian. And you basically, that's the mathematical equation. This is how you would find it in math. It's like this delta U equals F on some domain. And most people would be like, what does that even mean? Now, under the hood, what would actually typically happen is you define some form, and you'd have to get some compiler or something to change that into code, and then you'd have to assemble it and solve it and do all these sorts of things. Well, in Python, this became a very easy problem, where we just defined our element, and we gave these functions and whatnot. But then, so you see this first part, we're defining the types, like what the functions are, this trial and test. It doesn't really matter what they are, but just to know that they're special functions. But in the next part is something a mathematician can read. It's this dot grad times dx, which is actually the same thing that delta u is saying. And so immediately we were able to give this to mathematicians, who were able to then take it and do all sorts of much fancier things and eventually get to the heart simulations and so on and so forth. And just that inserting of the domain-specific language a little bit In Python, you can totally take over like the syntax of the language. It's sick, the number of things you can do there, but it's also fun. Remember, danger equals fun. But this is definitely a case that's driving innovation in the research space. So that's kind of my third example from kind of the research world. What does this mean for PyData? So now, as you've noticed, I've switched over much more to the data analytics world. And if you look at the data analytics world, this is a nice slide that Christine Doig, who's in the audience somewhere, put together for me. And it shows kind of like what's happened in the kind of like the ecosystem. We have like scientific computing that's been solving a lot of these big data problems for a long time. We have machine learning that mathematicians are starting to play around with data. Well, they're doing it for a while, but they've started to get really serious about large amounts of data and real computation. And so they're using the scientific computing tools. But then you have the business world over on the other side that they have distributed, fault-tolerant distributed systems and BI and database tools. And so they're going to hit the real world with these things like their SQL queries or their massive amounts of data they've pulled out of some customer engine, and they want to dump into some place to actually work with this. And so you have this complicated interaction between the actual complex analytics and the analysts who are on the ground gathering data and also trying to make sense out of all this data. And so we do what I've done in many times is come in and insert a Python layer to talk to these very complicated systems in many ways. We call this Blaze. And so Blaze is kind of a way to talk to all different parts of this and manage the communications in Python in a way that can then make use of those systems. And I like architecture diagrams, so this is another bad architecture diagram. So the way we kind of handle that is we have an API. For example, the Pandas API and the R as an API are both really good APIs that a lot of people have learned and can drive a lot of analytics. But in that, we actually grab the code and turn it into a deferred expression. So now I'm not going straight to my system and expecting the programmer to understand that you can't just run a massive solve on the system and expect it to be fast. It would be better if you filtered down before, or all the kind of the complexities that go into matching both the API to the data. And we have a layer in there so we can actually have a compiler and an interpreter that will grab your expression and get the best code to your exact system that you're using. And then on the far right is actually what we really care about is just the data and the compute layer. And time it shows again that you can give people that data and compute layer, but unless you teach them the principles of of computing and mathematics, they often will create big hairballs. So by putting a few APIs and making it so that they don't have to worry about that changing ecosystem, that whether you're using Spark today or Hadoop today or Disco or some other thing, we can actually make the same API talk to many systems. And so that's kind of like the evolution of like doing the research world. And now Blaze is kind of coming online and has a lot of users, especially in the academic world, just because it gives that same flavor, that super glue, and that complex interactions inside the ecosystem. So on the research world, I spelled Andreas' name wrong. Sorry, Andreas. But here's some academics that like I draw a lot of my inspiration from physicists to computer scientists, mechanical engineers, and mathematics. Grab my slides later. Go check out their blogs. They're awesome. But which kind of brings me to the end of my first spiel on Python and research. Is there any questions on that first too long ranting talk? Awesome. Cool. You guys are gotta liven up a little. Maybe. All right. So the next thing I want to talk about a little bit is now we have a huge ecosystem, and we have a lot of people who are contributing to our ecosystem and building on. And so there's a few challenges that we've kind of faced, and that NumFocus is kind of trying to help address in different ways. And those challenges, I just want to talk about these three challenges and kind of ponder some thoughts on ways we can help keep this innovation of Python alive and the Python data ecosystem. The first challenge is keeping code alive. What happens when you don't maintain code? Does anyone know? Rots, that's right. Entropy, good one. Bit rot, for example. I like to compare it to a house. So you can't see. I hate these projectors. So this is a house that's falling down in the middle of a jungle. I enjoyed one of my researchers one of my friends who's a researcher got into an argument with his boss about whether you need software, and he's like, isn't the software done? And he's like, well, are you done eating? It's also, it's like maintaining your house. It's like my weekends used to be coding. Now it's mowing lawns and chasing rats out of my shed and things like that. And so the same sort of thing happens with your code. And so the important thing, but the important part of this is that software really is an expression of the people who build it, and where are those people going, and what are they doing. And at least in the research world, there's kind of four major areas that the code gets built. And you can't see it on this here very well, but in the top I have the Department of Energy, and the Department of Energy funds a lot of complex scientific codes. A lot of the bread and butter of like LAPACK, which runs all your recommendation engines and runs all your linear algebra routines, was written at the Department of Energy. Then there's instruments, like at the top right, I have the nice telescope in Chile, where you can, if you're an astrophysicist, is like the nice place to go and have great views, but you are quite lonely because they have to put these out way away from people who spread too much light. And so, but these guys, they need software to run these huge systems. And a good advocate for this is Joshua Bloom, who has gone and used Python to actually make robot telescopes, where since these things are so far out and they're hard to maintain, it's hard to find staff to pull these things in, they use Python now to run the entire ship of many of these telescopes and so on and so forth. But like a lot of instruments, you look at CERN, you look at Fermilab, and so on and so forth. Down on the left is actually a supercomputing center I used to work at, and where they employ lots of scientists to help people run on big machines. Because it's one thing to write code on your laptop, it's another thing to write code that actually works on a parallel machine at scale and in an efficient way. And so there's a lot of people embedded in supercomputing centers to help people port their code so they can actually solve the real scientific problems at scale. And then the last one's XKCD's. Oh no, this is PhD Comics, National Postdoc Appreciation Week. And in academia, if you're going to write code, you're very few people get into a professorship position by writing code. Never mind that that's the thing driving the innovation in a lot of the work going on today. So there's this army of postdocs or research scientists and so on who work in this underpaid profession to get things done. And essentially what's happening in almost every one of these places is that the staff are realizing that, hey, I can write code here, or I can join, for example, the Google bus and get on the big data bandwagon and keep moving in that realm. And so it kind of stops some of the innovation that happens because of the way these structures have come together. Now, nothing against Google. They've done a lot for the ecosystem. Have given a lot of code back, but it's this kind of natural I think my friend Jay Vanderplas calls it the big data brain drain, which is fun because he wrote that blog and then I joined left academia, so it's nice. But essentially, what's happening is these coding projects, like everything I talked about here, involve mathematicians, involve physicists, involve engineers, and these people usually come from different places and they have different legal structures. And makes it very difficult to collaborate on these projects. And if you go through traditional academic routes, you're really only going to see a very small amount of money get to those folks. The salaries are growing at companies, and everybody who can code can kind of go through the code cycle. But also the fact that the scientific software writers leaving, it also impacts how much money actually goes back into the software. And to give you kind of a case study, how many people have heard IPython? Awesome. How many people know, like, who develops IPython? Is anyone? So, who develops IPython? So Fernando, that's Fernando and Brian. That's one answer. Another answer is Microsoft, right? Microsoft gives them a lot of money. Another answer is Berkeley or UC Poly, which are the employers of of these guys. Another answer is something like this, nature. So nature came in and Rackspace has given them a lot of resources to kind of put things together. So the real answer is a community, a very large community that has two leaders at the point of it, and it's become so important that magazines like Nature have started publishing their journals and analytics in it. But the team, it's on 2 continents, 4 academic institutions, and several companies. And so how do you manage this very wide kind of challenge of people? And I think the other thing to say, if it was only those academic institutions, the amount of money they would see that flows in would be around 30%. I think that a lot of people are shocked, like how little money actually. So you'll see big research dollars, but chop that down to 30%. That's how much actually goes to the researchers. And so this way that we're building our infrastructure to innovate is just kind of an old system. Now, my viewpoint is that the data science community is a very diverse set of jobs. From that very first kind of slide with these three different Venn diagrams, those are actually, it's a problem because those are 3 different career paths. Those are 3 different ways of thinking. That's just a lot of friction, but something that is vital to being solved in so many places that we're actually moving forward with it. And so if we want to have open code projects and open communities, we have to manage that complexity. And this is kind of where iKnown Focus was built. We noticed there wasn't really an institution that's coming along that's going to solve those problems, and so we created a new one. I think another big problem that people have is making our codes usable legally. There's a comment on the last talk about, we are a heavily regulated industry. How do we make these things legal? And the answer is that, well, there's not a single answer. There's definitely opportunities in academia, and there's opportunities in industry, and this is one place where industry helps a lot to come in and help manage those legal entities. I think I hear a lot of people talk to me about Palantir and how Palantir is using the SciPy ecosystem and making tons of money off the government because they leak their price sheet and so on and so forth. But my viewpoint is like, hey, Palantir is doing a really good job of getting open source software in the government and actually supporting the government in ways that you just couldn't as a grad student. Is my time 5 minutes? Okay. So just to share my story, like I started out with the GPL community. The GPL community was like really like, I don't want companies to make money off my code. And after kind of being sat down and being told, well, that means that all these other people can't use your code. And so, well, I really want to create innovation that helps the entire world. And companies have a role in that, as well as governments, as well as academics. So I switched over to Little Devil Man, which is the BSD license. I love it, it's Little Devil Man. It's just like, okay. But the BSD license, is just kind of like freedom. Like that was like, GPL was freedom, but it was actually freedom that made everybody participate in the freedom the same way. The BSD was kind of, I don't really care. Here's a few rules. Just I want you to know who wrote the code. And that works really well for communities to get together, so it lowers the barriers to get together. But then this idea of software patents came up. And being able to protect yourself against software patents to use open source codes became something of an interesting kind of way of interacting. And so the Apache license has a patent indemnification. It's basically the BSD plus a patent indemnification clause, which has done wonders for their community and had an explosion of kind of the data science world through the Apache organization. It's one of the reasons I believe like so many data science stuff comes out of the Apache Foundation. But that's really, in my view, the simple problem. The much bigger problem is how you actually share data. So if we're going to have an open code base, I was at Tika, which is this big parsing library. They have people inside companies who donate. They actually donate the bug reports. They don't donate the data because they can't share the data because data is very tightly held. That's the actual information of your company. But we need some way to share like how your computer works, how this program works on your data, where are the bottlenecks, what slows things down, and so on and so forth. And so data is a huge problem. And I'll end with this last one is keeping code interoperable. There's this great paper by Kathleen Fisher on the next 700 data description languages. Most people didn't even know of one data description language, much less the next 700. So data is the new, like my kind of buzz there is that data is the new operating system. We need to make sure that we can use data in different ways and our code can work around that data. And I'll just jump off here. So in a few observations as research goes forward is like making sure your code process is open to forms of communication. Being usable and interoperability is really crucial to our community to make this community thrive and get the researchers and the innovations that they provide involved in the community. So thank you very much for your time, and here's my Twitter ID and my info again. Thank you very much.